Hello everyone. In this tutorial we explain how to compute, or better to say how to evaluate double integrals. And let's immediately start with an example. Compute the value of the integral given over here, where R is the region bounded by two parabolas. Here's the first parabola and here's the second parabola. Let's solve this example. The first step is to sketch the region R in the two-dimensional plane and to mathematically describe this region. So how to do that? Well, to sketch the region R, we first need to find the intersection points of these two parabolas. To find the intersection points, we need to solve this system of equations. The first equation in the system is y is equal to 2x squared, and the second equation is y is equal to 1 plus x squared. How to solve this system? Well, we have y on this side and y on this side, and we can simply say the first equation is equal to the second equation. So we can write 2x squared is equal to 1 plus x squared. From this equation, we have that x squared minus 1 is equal to 0. This is a quadratic equation and we need to find its zeros. The zeros are obviously at x1 is equal to plus 1 and x2 is equal to minus 1. If we now substitute x1 in any of these equations, we will obtain that y1 is equal to 2 multiplying x squared, that is 2 multiplying 1 squared is 2. Similarly, we can find y2. y2 is obtained by substituting x2 in any of these equations. That is, if we substitute x2 is equal to minus 1 in the first equation, we will obtain that y2 is equal to 2. Perfect. Now we are ready to sketch this region in the two-dimensional plane. First of all, let's draw horizontal and vertical axes. This is x and this is y. So let's sketch these intersection points first. Okay, we have that x1 is 1 and y1 is 2. So let's take the measure. So for example, this will be 1, and symmetrically this will be minus 1, and then 2 will be somewhere here. Consequently, our first intersection point is here, and the second intersection point will approximately be here. And let's write these intersection points. So this intersection point is minus 1, 2, and this intersection point over here is 1, 2. Perfect. The next step is actually to draw the graphs of these two parabolas. So let's do that. Let's change the color over here. First of all, let's draw a graph of y is equal to 2x squared. When x is 0, y is 0. Consequently, this function starts from here, and we simply need to draw a parabola. The parabola obviously need to pass through these intersection points. So let's nicely draw this parabola. Here it is. Let me try to do it nicely. You can do it even better if you're using pen and paper, and my suggestion is to do everything by using pen and paper. So here it is. Beautiful. So let's sketch another parabola. For that purpose, I'm going to use a different color. Another parabola has equation 1 plus x squared. When x is 0, we start from 1. That is, we start from here. And here is our parabola. Again, this parabola has to pass through these points, so we have to be very careful what we are sketching. So here's the one branch, and here's another branch. They should be symmetric. Okay, not bad. And to avoid any possible confusion, let's write equations next to the curves, that is next to our parabolas. This parabola over here has the equation y is equal to 1 plus x squared, and this parabola over here has the equation y is equal to 2x squared. Perfect. The region R is bounded from the top by the parabola y is equal to 1 plus x squared, and from the bottom by the parabola y is equal to 2x squared. And let's sketch this region in the plane. Here it is. It looks like this. I'm using over here vertical hatch. However, you can also use horizontal hatch, or you can even use a cross hatch. Perfect. Over here, for clarity, I draw the graph again and I sketch the region. Here is the region R. In order to solve our original integral given over here, we need to know how to mathematically describe this region. In mathematics terms, the region is a set of points. That is, for example, you can see first point, then you can see a second point, third point, and you have an infinite number of points in this region. Every point has coordinates x and y. Let's mathematically describe this region. We write R is, it's a set, consequently we use the notation for a set, and it consists of points with the coordinates x and y. Then we need to specify that these coordinates have to satisfy some properties, that is, they are not independent. From this graph, we can see that the coordinate x of any point, for example of this point, is in the interval from -1 to 1. This is because these intersection points are actually the boundary points, and their x coordinates are -1 over here and 1 over here. Consequently, any x is in the interval from -1 to 1. Consequently, we write -1 is less than or equal to x, and x is less than or equal to 1. Perfect. How about y? Well, let's consider this point over here. Its y coordinate is actually going from here, that is from this boundary to this boundary over here. If the coordinate of this point over here, for example, is x, then the coordinate of any point on this line is also x. However, the coordinates of the points y are in the interval from this lower parabola to the upper parabola. Consequently, y has to satisfy this. We have that y is in this interval. Let me write the interval so I will explain it once again. We can see that over here we obviously have 2x squared, since this is the lower parabola, and over here we will have 1 plus x squared, since this is the upper parabola given over here, and we close the set. So let's repeat. 2x squared is less than or equal to y, and y is less than or equal to 1 plus x squared. That is, the y coordinates, when x is fixed, are from this parabola to this parabola, and the lower parabola has this equation, 2x squared. That's why we have 2x squared over here, and the upper parabola has an equation 1 plus x squared. That's why we have here 1 plus x squared. Now we are ready to solve our original integral. Let's write it again. Integral is equal to the double integral over the region R, and the function is 2y plus x. And over here, listen carefully. We can split this integral like this. First of all, we will have an integral over x, where the boundaries from x can be seen over here in this set. The boundaries are from -1 to 1. Then we have the second integral, and this integral is over y, and the boundaries are from 2x squared to 1 plus x squared. And then over here we have the function 2y plus x. And then instead of dA, we write dA is equal to dx multiplying dy. However, we are going to match the integration order over here. Since we will have this inner integral that depends on dy, and consequently over here we will write dy, and then I'm not going to write parentheses here, however the parentheses exist here, and then we will have dx over here. To avoid confusion over here, I'm just going to use bars over here to denote that this integral is the y integral, that is the integration with respect to y, and this integral is integration with respect to x. Now listen carefully. In this inner integral, x is considered as a constant. That is, over here we assume that x is fixed. We are going to integrate later on with respect to x in this outer integral. Also in these bounds, over here and over here, x is considered to be fixed. So when computing this integral over here, and let me use these dashed parentheses to make sure that you understand what's happening, that is, when we integrate this integral over here, x is simply considered as a constant. This is very important, and we only integrate with respect to y. Once we do that, we will obtain the expression that only depends on x. Why? Why is that? Well, because y will be substituted by these bounds. And then the resulting thing will only depend on x. Another nice thing over here is that we substituted dA by dx dy. Now, loosely speaking, what's happening over here, if you take any small region over here, you can roughly say that the area of this small region is simply dx multiplying dy, since this is a squared. Consequently dA, or the small area, is dx multiplying dy. However, this is not completely mathematically correct. However, it's still a very good method for remembering how to substitute dA. To repeat again, dA is substituted by dx multiplying dy. Now, what do we do over here? We have this inner integral that should be integrated with respect to y, and x is considered as constant. What's happening over here? The bounds are from 2x squared to 1 plus x squared. Once we compute this integral with respect to y, the resulting expression will only depend on x, and we will be able to integrate with respect to x, and then we will obtain numerical values. Here is our integral, and let's solve it. First of all, over here I'm going to write the outer integral, since we are not integrating currently with respect to the outer integral. And let's solve the inner integral. Over here, again, x is considered as a constant, and we are integrating with respect to y. Integral of 2y becomes 2y squared over 2, and we have the bounds. The bounds are from 2x squared to 1 plus x squared. Then what do we have over here? We have plus, x is constant. Integral of a constant dy becomes that constant multiplying y. Consequently, we have x multiplying y, and over here we have the bounds from 2x squared to 1 plus x squared. And over here, don't forget that we are left with dx, and that's it. We solved the inner integral. The next step is to substitute the bounds inside of this term over here. And I rewrote this term over here, and let's substitute the bound. 2 and 2 can be cancelled over here. And let's see what do we have over here. We are left with y squared. And let's write it, y squared. And let's write the bounds again. Don't be lazy to write, since it's always a good idea to practice writing and to practice to stay focused for a long time. This will help you in solving more complex mathematics problems. And let's substitute the bounds. So let's see what do we have. We have y squared, and the lower limit is 2x squared, and the upper limit is 1 plus x squared. First of all, we need to substitute the upper limit. So we will have 1 plus x squared minus, what do we have here? We have minus 2x squared, then squared. This becomes minus 4 x to the power 4. What do we have here? We have x multiplying what? We have x multiplying upper bound, 1 plus x squared, and then we have minus lower bound, 2x squared. Perfect. And let's perform the multiplication. Let's see what we have. We have from this term over here 1 plus 2 multiplying x squared plus x to the power 4 minus 4x to the power 4. And what do we have here? We have plus x to the power 3. We have minus 2x to the power 3. And let's group the terms and let's calculate everything. We see over here that we have x to the power 4 minus 4x to the power 4. This becomes minus 3x to the power 4. Then we have x to the power 3 minus 2 multiplying x to the power 3. This becomes minus x to the power 3. Good. How about the other terms? Well, over here we have 2 multiplying x squared. Consequently, we will write plus 2 multiplying x squared. Perfect. And let's see other terms. We are left here with x, and we are left with 1 plus x, and then plus 1. Perfect. And consequently, our original integral becomes this. Let's denote it over here to be I, to be our original integral, and it becomes this. It becomes a simple integral from minus 1 to plus 1 of this expression over here. We have minus 3 to the power x 4 minus x to the power 3 plus 2x to the second power plus x plus 1. And over here, we are integrating with respect to dx. So let's solve this integral. Let's integrate the first term. The first term becomes minus 3 over 5 x to the power 5, and let's immediately put the bounds. Minus 1, 1. Then the second term becomes minus x to the power 4 over 4, and let's put the bounds, minus 1 to 1. Then we have plus 2 x to the power 3 over 3, and let's put the bounds from minus 1 to 1, plus x squared over 2 from minus 1 to 1, and then we have here plus x with the bounds from minus 1 to 1, and that's it. Let's analyze this expression. Over here we can see that this term will be equal to 0. This is because we have x to the even power. And when you have x to the even power or even function and bounds are from minus something to plus the same thing, then this term is 0. The same applies to this term. This term is also 0. And we are only left with this term with this term and with this term. So let's write over here. Our integral becomes minus 3 over 5 x to the power 5 with the bounds that are from minus 1 to 1. Then we have this term plus 2x to the power 3 over 3 with the bounds from minus 1 to 1, and we are left with this third term plus x with the bounds from minus 1 to 1. And let's substitute these bounds. We have minus 3 over 5, and what do we see over here? We have 1. We will have minus 1 becomes plus 1. Then we will have plus 2 over 3. What we will have inside, we will have again 1 minus 1 becomes plus 1, and that's it. And over here we will have again 1 minus 1, and this becomes plus 1. And finally we will have the expression that will look like this. We will have minus 6 over 5. Then we will have over here plus 2 over 3 multiplying 2. This will become 4 over 3. And over here we will have plus 2. You can easily verify that this expression is equal to 32 over 15. And that's it. We were able to successfully solve our double integral.